Hello. Now we'll calculate the potential change across a real battery. As we all know that real battery consists of internal resistance. So this is the internal resistance. So when we have a real battery, we bring that internal resistance outside of the real battery just to show it. This whole structure is a real battery. So this real battery we are dividing into ideal battery plus the resistance. We are keeping this resistance outside. So when we'll be talking about this whole battery, it's the combination which is the ideal plus resistance. So we want to calculate the potential change, and we already know how to calculate the potential change for ideal portion of the battery and for the resistance separately. So combination, the potential change across this whole structure will be the potential change across the real battery. Okay, so we'll make two cases here. In case of real battery, we make two cases. Case one is for charging. So when the battery is being charged, that will be the first case. When the battery is being charged, at that time the current goes inside the battery, meaning current goes inside the positive terminal of the battery. This is a case when the real battery is being charged. And the second case will be case 2, when the battery is being discharged. So when the battery is being discharged, in that case you will see that this is a real battery. So when the battery is being discharged, current will be coming out of the battery. Okay, so that will be the case when the battery is being discharged. So either the battery will be giving the current or the current will be going inside the battery. These are the only two cases which will be happening with any battery, either it is ideal or the real. In case of ideal, it doesn't matter. When we calculate the potential difference across the ideal battery, the potential change across the ideal battery is independent of the direction of current. But in case of real battery, we will know that in case of real battery, the potential difference across the real battery, it do depends upon this direction of current. Okay, so in this case, we'll calculate the potential difference. And this point I'm defining as A and this point I'm defining as B. So potential difference across A and B will be the potential difference across the real battery. Okay, so first we'll move from A to B and then we'll move from B to A and we'll calculate. So when we are moving from A to B, so first we have to cross this ideal portion of the battery. So when I want to move from A to B, the final point is B and the initial point is A. So we'll be calculating the change for final minus initial. So I'm calculating VB minus VA. Okay, so when I want to start from A and want to move till B, I'll be crossing this battery, ideal battery, which is having the voltage, or we can say EMF across it equivalent to E. So we are moving from positive terminal to negative terminal. When we are moving from positive terminal to negative terminal, we are moving from higher potential to the lower potential because it is having positive charge. So corresponding to positive charge, it's the higher potential. Negative charge means lower potential. So we are moving from higher to lower potential. So when we are moving from higher to lower potential, the voltage across this ideal battery is E. But since we are moving from higher to lower potential, it will be minus of E. That is minus of E. Now we have to move across this internal resistance as well, which we define as small r. So when I'll be moving through this internal resistance, so I am moving, you see in this case, I am moving in the direction of current, which is I. So when I'm crossing, in this case, when I'm moving from A to B, so when I cross this internal resistance, I am moving in the direction of current. So when I'm moving in the direction of current, the potential will decrease because current moves from higher potential to lower potential. So this point will be having higher potential and this point will be having lower potential. So when I'm moving from higher potential to lower potential, the potential difference magnitude wise it is IR. We already know that. Since I'm moving from higher to lower, it will be minus of IR. So this VB minus VA will be minus, we can take common, E plus IR. This is the potential change when we are moving from positive to negative terminal of real battery. Now let's check if we are moving backward. So if I'm moving from negative plate to positive plate from B to A, I'll be calculating VA minus VB. We can calculate this VA minus VB by just reversing this thing, but I want to just check it here. So I'm moving from B to A, I'll be crossing the resistance first, opposite to the direction of current. So when we move opposite to the direction of current, potential change is positive plus IR. And then we will cross this ideal battery. from negative terminal to positive terminal. So it will be plus E. So this VA minus VB becomes E plus IR. So you can see this value, magnitude wise, this value is more than E. So this idle battery of this real battery would have been the idle battery. EMF across the idle battery is E, which is the maximum strength. But in case of charging, the voltage applied across this real battery is more than the EMF of the battery, and it is logical as well. So if you want to charge a battery, you have to connect this real battery with some stronger battery, which will be having voltage more than the EMF of this battery, which is E. So that's the value E plus IR. So voltage across this real battery will be E plus IR. And that's how it will get charged. Okay. Now let's come back to this discharge segment. So when this real battery is being discharged, so we are drawing current out of this battery. In this case, again we'll do the same process. This point is A and this point is B. So in one case, we'll be moving from A to B, meaning from positive terminal to negative terminal. In other case, we'll be moving from negative terminal to positive terminal. Okay. So when we are moving from positive terminal to negative terminal, first we have to cross this idle portion of battery. So I'm moving here to here. The final point is B, initial point is A. So we will be getting VB minus VA, final minus initial. So first we will be crossing this idle battery from positive terminal to negative terminal. So potential difference across this change, across this segment will be minus of E, because we are moving from higher potential to lower potential. Magnitude wise it will be E, but since we are moving from higher potential to lower potential, it will be minus E. Then we have to cross this resistance. And when we are crossing this resistance, we can see we are moving opposite. Current is in this direction. And we are moving opposite to this current. The value of current is I. Since we are moving opposite to the current, we are moving towards the higher potential. So minus E plus of IR. That will be VB minus VA. So we can write VB minus VA is equals to, I can take minus common, E minus IR. Now let's move from B to A. So when we start moving from B to A, first we have to cross this resistance. So when we move from B to A, we are getting VA minus VB. This is the final point, this is the initial point. So when I cross this resistance, internal resistance, I am moving in the direction of current. So when we are moving in the direction of current, potential decreases. Okay, so I'll be writing minus of IR here. And then we have to cross this idle portion of the battery, which is from minus plate to positive plate. So potential difference will be plus E. So this whole value also becomes E minus IR. So you can see the magnitude wise, these two values are same. Okay. So this VA minus VB becomes E minus IR. And as you can see, this value is less than E. So when you have a real battery, and EMF of the real battery is E, which is the maximum strength that battery is having. But since it's the real battery, it is having some internal resistance. Then due to the internal resistance, in case of discharging, the voltage across the real battery comes out to be less than the maximum of strength, which is E minus IR. So in both the cases, if you are having a real battery, then in case of charging and in case of discharging, you get different values of voltage depending upon the direction of current. So in case of real battery, voltage across the battery depends upon direction of current, so we have to take care of that. So whenever we are applying a Kirchhoff law and we are calculating the voltage across the battery, that real battery, we have to think about the direction. So according to the direction, we will be calculating the potential change. My advice will be, when you are applying a Kirchhoff law, apply it separately. Move like that. So when you are, meaning for idle portion of the battery, calculate it separately, and for the internal resistance, calculate it separately. You should not be memorizing this formula basically, because when you memorize the formula, you might make some mistake. Okay? Okay. Thank you.